Welcome to my playlist for the Fourier and Laplace transforms. If you've ever used a Fourier or Laplace transform and then afterwards thought, I don't understand what I just did, I don't understand where the equation comes from, I don't understand why it works, I don't really understand how it works, and I don't really understand how it gives me this answer, then this video playlist is just for you. If you like the playlist, then please subscribe or leave comments or likes or dislikes. It's much better if I can get some feedback and get some interaction on the videos that I do, because it makes the whole thing just a bit more fun. Now, the idea of the playlist was to understand the Fourier and Laplace transforms. So I wanted to have a good foundation, a good basis. So I was sitting back and thinking, where exactly am I going to start from? What's going to be my starting point? Now, I decided to start with the Taylor polynomial. Now, if you don't know what that is, it's in the videos. But I decided I wanted to derive the Taylor polynomial. So I go through, and the very first point is the derivation of the Taylor polynomial. Now, from the derivation of the Taylor polynomial, I can then go and use the Taylor polynomial to then derive the Euler identity. Now, the Euler identity has been called the most beautiful equation in mathematics. It's e to the I pi equals -1. So from the Euler identity, I can then use that to produce the complex exponential. The complex exponential is the most basic constituent part of the whole ideas of our Fourier and Laplace transforms. The complex exponential is also described in MATLAB. So I've got a nice MATLAB simulation, and they say a picture paints 1,000 words. Well, it's really true in this instance. So that simulation will break down the complex exponential into its constituent parts, the sine and the cosine parts. So it's well worthwhile having a look at that. From the complex exponential, I then go on and I derive the Fourier series. Now, I derive the Fourier series initially in a graphical format. So I have been using this book here, Transforms and Signals and Systems by Peter Kanalskis, and it's got a lovely graphical approach to the derivations of the Fourier and Laplace transforms, and if you can get a hold of a copy of that, then I would highly recommend that you have a look at that book. Now, not only do I look at the derivation of the Fourier series in terms of a graphical approach, I also look at the Fourier series in terms of functions as vectors existing in infinite dimensional vector spaces. Now, that all sounds a bit difficult, but it's not really, and it's all described within those 3 videos in the derivation of the Fourier series, and it's well worthwhile thinking about the Fourier series in those terms, because once you get your head round about that, it's a very useful piece of mathematics that you can then go on and apply to other areas of physics and engineering. I then go on and I derive the complex form of the Fourier series, and from the complex form of the Fourier series, I then go on and do an intuitive graphical derivation of the Fourier transform. Also, throughout these videos, I have a lot of MATLAB simulations. Now, I made a bit of a boob because I stuck the MATLAB simulations at the end of a lot of the videos, and I could have probably helped my audience retention if I'd put the MATLAB simulations at the beginning. So future videos I'll probably start doing that. I've also added in a few extra videos using an online graphical calculator called Desmos, that's D-E-S-M-O-S, and I've left the simulations in the comment section at the bottom. I've also got a set of videos describing lots of the properties of the Fourier transform, for example, time and frequency scaling, duality, convolution, the Fourier transforms of differentiation and integration, and looking at the symmetry of the Fourier transform. The second part of the course is on Laplace transforms. Now, I go through a graphical derivation of the Laplace transform, and I think about the Laplace transform as an extension to the Fourier transform. So the graphical derivation again comes from this book, and it's well worthwhile if you can get hold of the book to have a little look at it. But I go through the graphical derivation also in MATLAB, so I work through all of the component parts of the Laplace transform, and I put them all into MATLAB, and you can see them all in glorious 3D Technicolor. I also go through another couple of derivations which are more mathematical derivations of the Laplace transform, and they're worthwhile having a look at. I then look at Laplace transforms of some fundamental functions like the real and the complex exponentials, and also do those in MATLAB so you can see the full derivation in a graphical 3D intuitive manner. I look at differentiation and integration in terms of Laplace transform and the initial and final value theorems, and some of the symmetries of Laplace transforms. So there's 41 videos in the series, and each video moves along in a sequence one after the other.